Good morning, mathematicians. Welcome to another office hour. Hope you're doing well. Start of a new week. Start of a bunch more theorems to prove. Oh, I gotta go open up chat. I didn't think about what I was going to talk about today ahead of time. I should have. Hey, Edit Smith. So, I don't know. I guess I'll just open up... oh, hello. Quality. Oh, quality content. Nice. Yeah. I guess I'll just open up the notepad and start doodling random math stuff till the questions start pouring in. Well, we've got this paper in front of me here that I've been looking at. Still working on that preprint. And, well, assuming the Kasdan-Lustig hypothesis, we proved this conjecture here. So I was going back to see the way things are originally stated and some of the, initial considerations around this concept. So I can put more history in the document. Okay. What do we got going on here? Well, recently I was ranting a lot about modules, so I could keep doing some ranting about modules to get us started. Although I guess I said the main thing I wanted to say was, oh, good morning. Good morning. I wanted to talk about this thing about centers of categories in the rings, but that's pretty much dealt with already. How do I get more of these fancy pens? I just got one at a time? That's fine. Yeah. What should we talk about? Well, one thing I was reading up for fun that I really don't know a ton about is the Dold-Kahn correspondence. Where one takes a simplicial, abelian group, and shows that those are equivalent to, you know what, I write better with this other pen anyways. And that those are equivalent to, I think, non-negative chain complexes of abelian groups. And part of the reason why I was looking at this is because I'm trying to better understand infinity categories. And in particular, there's a way to view a derived category of some abelian category as being some kind of quotient of some, this is definitely not standard notation, but let me write dA for some infinity category version of the derived category. But somehow this is maybe more natural, whereas this is just a triangulated category and it doesn't really behave well under like limits and tensor products and stuff. But I've been told that the infinity category version apparently is much better behaved. So that's what I've been looking at. I do have a book here on yeah, I got this book online because when I log into chess.com, it keeps advertising me books that I really want. That it's really locked in with. I mean, some of the ads I get on certain websites, Reddit or Facebook or something, I'm like, I don't know, not hitting the mark. But I will say, kudos to the ad algorithms for knowing exactly what I want in terms of textbooks. The yellow books, yeah. Do I normally read grad textbooks from start to end? No, I don't think I've ever read a book. I don't think I've ever read a textbook in my life start to end. To be honest, I don't think there's a single textbook where I can confidently say that I understand every. Well, no, that's not true. I mean, there's probably textbooks out there where I could say I understand everything, but I don't know if I've ever read any textbook cover to cover. It's certainly not done every exercise. Sometimes I feel guilty about that. Sometimes I feel like I should have. Like, I probably should have read Bushnell and Enyart's book on the local Langlands for GL2. I feel like that was a book. That's a book I probably should have read cover to cover. Or maybe Getz and Han would be a good one to read cover to cover now. But yeah, the truth is, I don't know. It doesn't seem like there's time in the day, in the life, to read a whole textbook cover to cover. Yeah. I would say there's certain sections, certain chapters of certain textbooks I'm quite intimately familiar with, let's say. But well, yeah, okay. I'll talk about how I process this in a second. But yeah, it's also like yeah, no, like I said, I do feel guilty. I do sometimes feel like, well, I really should go back and read these things in more detail. But yeah, so it's like, first off, sometimes like, if you need something for very specific research purposes, it's just not gonna, you don't have the time. But even reading things for enjoyment, I mean, then it's like, I don't know. Then it seems even less likely. Like, you just want to go read the fun bits. But then when I do read things just like for fun as well, I sit down and make myself do things I don't necessarily want to. How often do I go back to learning undergrad stuff? I read on Reddit that it might harm your research, especially when it's kind of unrelated. But I don't really see that, to be honest. Yeah, I mean, this is the great thing about TAing courses in grad school, and especially, like, I always make a point to be a TA for the more difficult courses. There's more work on my end for grading. It feels like more work anyways. But the advantage is the material's more interesting and engaging, right? If I'm like TAing analysis 2, for example. And then you also get to like really review stuff. I also got to straight up teach a Galois theory course the fall before last fall. And I That's when I really learned Galois theory. I mean, of course, I'd done some Galois theory before, but it's different when you need to. You get a deeper understanding when you get to the point where you need to deliver lectures and design a course. You need to understand it well enough to really explain it to other people. So, but yeah, even just in TA positions, it's like you gotta, if you're running a tutorial for your students or something, you need to go back and you might need to review some things, and it's great. I love it. I don't know how often I need to go back and review undergrad things for my research, because it's pretty beyond a lot of undergrad stuff, but yeah, it's more of a lot more a lot more of new learning, I would say. What about this book on my screen, and what portions and process do you digest it? Well, I haven't spent a ton of time with this book yet. But, so the first thing I do is I sort of look over the table of contents, and I'm like, okay, what are the things that I really need to know? I mean, yes, it would be, first off, I'm not even reading this strictly for research purposes. I mean, I kind of am. The sort of modern categorical local language is all in the language of infinity categories. And even some of the derived category stuff, I'm just kind of motivated by the fact that maybe some of the stuff I do with derived categories will be easier if I learn how to work through this approach, right? So I'm sort of looking over the table of contents. I'm like, okay, probably most of the things here are actually useful for me, right? I mean, limits and colimits, part of the idea of using infinity categories, one of the ideas is that they offer better behaved limits than ordinary derived categories. Probably adjunctions, those are always useful. Yeah, I don't know as much what's going on in chapter 2, and stuff doesn't stand out to me as interesting immediately, but okay, probably I need to read it. I mean, the main thing for me here is really 1.1 and 1.2. I really want to understand these two in detail, right? So, I mean, obviously you want to read the motivation and overview. And yeah, I've sort of, so I don't know, I've gone through, again, I haven't spent a ton of time with this book yet, but earlier experiences with this book, I basically am just scrolling through and I'm reading things, maybe not necessarily going through any of the proofs in any complete detail, maybe treating it as just as bedtime reading. And then, eventually you get to some point where it's okay, but it's very hard to understand what you're doing here at some point, unless you bust out a pencil and paper and start going through it yourself. And or once the concepts start layering, you're like, oh yeah, I can't really get that much further. So then, I've gone back, and then I'm like, okay, let me try and, prove some of the exercises or follow through the proof in the book. One thing you should do is the proofs in the book are always, well, not always, but sometimes they leave out some details. And, one thing you can try and do is rewrite the proof in your own words and add some detail. That's maybe a good thing to try to do. In my research field, how much the materials in grad textbooks relate to current frontier research? For example, I don't know if solving textbook problems dealing with elements ideals still relevant. Since new papers I skimmed, just weird words and diagrams. Yeah, so, I mean, it's kind of a mix, right? Yeah, I mean, so solving textbook problems, I think it's just for me, in order to understand something, I can't just, and I think this is the case for everyone really, I can't just read it, you know? I need to actually do it, even if it's just following along the proof and writing it in my own words in pencil. So I do think even the textbook problems are still useful because, you know, it's sort of like a curated list of exercises that the author, you know, probably feels like, this is a good exercise to really, that helped them to digest these concepts, right? Now, as for research in my field versus grad textbooks, yeah, I mean, that's the thing is, oftentimes when you get to like cutting edge research, well, a lot of that stuff isn't in textbooks anymore, right? Textbooks, hello, take. Textbooks are things that are written about things that we sort of understand more. And I mean, there's textbooks that can help get you up to paces with modern research, right? People are writing new textbooks all the time, but the thing is, there just will be a lot of stuff that isn't in the textbooks because it's like daily the math is being developed. So yeah, when it comes to research, like eventually you just got to start reading papers. But that's also like the textbooks are still useful. I mean, so one, your like supervisor is going to help you understand a paper, or at least just tell you what papers to read, and then you have to do a bit of like careful selection on your own to try and figure out, okay, what are the like what things do I really need to take away from this paper? What tools, techniques should I really understand? Or am I just going to take the theorems and then use those theorems? Yeah. Yeah. But I mean, I have tons of textbooks that I consult all the time because I do need to remind myself of stuff. And also, like, your knowledge is imperfect. So, like, you know, I have this preprint coming out. Hopefully soon. I've been saying that for weeks now. And then I keep finding reasons to work on it more. But the thing is like, okay, so there's a bunch of things that go into that preprint. Like perverse sheaves, which I've talked about on this channel, and it's like, yeah, I know enough about them that I was able to write some proofs that I needed in the document, and you know, that offers some new whatever things to my research, but I'm by no means an expert in the topic. There's plenty of room for me to learn more and to better understand them. And so I'm going to continue to consult textbooks and the research literature as I go. But, you know, I don't need to be an expert to begin, you know, making research level statements that use those tools. But I've got at least now a baseline enough that I can use them. But I still have the understanding that, like, well, there's always room to improve. Same thing with other stuff to do with representation theory. Like, we're talking about the theory of generic representations. Where did I put that paper? Where's the other paper? Part one. No, this is part one of the paper, but where's... Oh, I think I had it in Google here. Yeah, so like there's this paper here about the theory of generic representations, and it's like, yeah, I know enough about them to sort of get by and to, you know, prove some things, make some statements. Actually, I don't even. I mean, the results in the paper say some things about generic representations, but it's really just stuff that we do on the geometric side. In this paper, the generic representations are just sort of on their own. So I don't even need to. I haven't even needed to use them in a very serious way in this paper, right? So certainly this is also something that like going back and understanding this this paper would be useful for me, just to have a better understanding of that theory. Like, yeah. So you can always be at a point where you can do research, but there's still more to learn. Oh, well, it's too bad you don't have as many people to talk with in your country about this, about modern algebra and category theory. But that is the wonderful thing about the internet. I mean, it's incredible the ways that people can connect on all sorts of different topics, including mathematics. Like, yeah, you might have, who knows? You might have never even discovered modern algebra or category theory if no one's taking it seriously. Yeah, it is interesting though. I do wonder, I mean, whatever, you don't have to say your country and dox yourself, but it is interesting that there's different sociological clusters of mathematicians, for one reason or another, various different demographics, could be, by country or whatnot, have different focuses on mathematics, or certain fields seem to be, are sometimes very popular in some countries and not as much in others. I mean, it makes sense, right? You have one or two serious people in a field at one of the largest universities in any given country, and so they're going to attract a crowd around them, and it very much makes sense that it grows out organically from that. But nonetheless, it's interesting. But it is also interesting to think too about how one's society and the general priorities of society could conceivably influence the kind of mathematics that one does. I mean, there could be of course, an obvious thing is some sort of worldview of practicality versus dreaming, as some, a crude, applied versus pure math sort of thing. But it's also very easy to imagine there's other things, like even just, I don't know, maybe analysis versus algebra, or other things like that. Like, I think the Hungarians have a lot of combinatorics, right? How did I start working in my field? I did not decide in undergrad. No. No, I basically, yeah. So basically I was just open to a lot of different things. I have a lot of different interests, and so I was just like, I'll be pretty happy wherever I end up. My master's, I went to, there's two universities in my hometown. I went to one for my undergrad, but I started like taking courses and hanging out at the other one at the same time. And I started talking to a professor there, and his research seemed interesting to me. So I asked him, if I could do a master's, and he said, yeah. So I applied, and that's how I got in there. And then, I applied other places as well. And then, yeah, that was sort of already in this direction. But, and then, yeah, I also just cast a wide net for applications for my Ph.D., just anywhere that seemed somewhat interesting to me. And, yeah, I applied a lot of places that had the word automorphic in the, research description. And then I ended up here. Do I know of a self-study material about the transition from Galois to class field theory? Maybe I should go learn algebraic number theory first. The little I know is from rings and fields. Yeah, you should probably go read algebraic number theory first. To be honest, I don't actually know enough that much about class field theory. Again, that's another one I should, as someone who works in Langlands, I should really know um, uh, more about class field theory than I do. But it's on the to-do list, and it's like, yeah, it is important for Langlands, but it's also like, well, there's so much I can do without needing to know that. But like, I technically use some of it. Algebraic number fields by Yanish is good. Okay, yeah, I'll believe you there. I watched your math talk video. Came to know you. It's a really interesting video. Great, awesome, awesome. Yeah, I haven't done an interview in a while. I probably should. What else about Galois theory? I'm trying to think about another. I mean, I really liked Marcus' book on number. Well, I guess that doesn't get into class field theory. One book I would really love to read more seriously, though, is Fourier analysis. There's so many books I want to study that I would love to read cover to cover, but Fourier analysis on number fields, by Valenza and Ramakrishnan, I think. It's sort of like somewhat analytically flavored. It's kind of like the goal is to do like class field theory, but in the language of Tate's thesis. So seems really cool. Hello from Argentina. Hello. Glad you're enjoying the channel. How do I see applied math in its current state? Some topic that you found interesting? I mean, traditionally, I never really enjoyed applied mathematics when I was younger, which I'm sorry that was the case now. I mean, it wasn't intentional. You like what you like, right? And as I'm a little bit older than, say, like the average, than like the typical grad student who goes right, high school to university to grad school. And starting to feel the burden of being a poor academic, and also so there's economic pressures, and then also I feel like in the last couple of years, for a variety of reasons, I've really come around on statistics, and I've been more interested in that. Just as a means of like, I mean, the gateway drug for me was through like abstract measure theory, and then I was like, whoa, there's really cool probability theory stuff, and then I started like, I don't know, it wasn't just that, but there's a lot of other things that built up, what I just sort of saw like the power in being able to like understand and manipulate the world around you according to like statistical laws, and I thought that was really interesting. Lots of little things like, okay, there was actually this Lex Friedman podcast where he had this woman. She was like an adult content creator, and she saw that there was like a lack of data about like people's sexual preferences and things like that. So she taught herself Python and statistics because she was like, well, I want to like just run more data and have more surveys and stuff. And I thought that was just so cool. And then, we learned more about the world. And I mean, who knows? Maybe she wasn't the best at data collection, or her things were really biased or something, because I think she did a lot of her stuff just polling on Twitter or whatever. But nonetheless, I thought it was so cool that she did that. And another one is an older movie I saw recently was Moneyball. But I just saw it for the first time recently, and I was just so enamored with this idea of like, yeah, using these statistics of like, oh, taking the percentage that someone gets on base, and that sort of overturned the traditional wisdoms, and is now like widely adopted in baseball. And I was like, wow, that's actually, a part of me that what never had interest in that sort of thing before was sort of like ignited by this possibility of like impacting the world around me using mathematics. Um, yeah, so I don't know. Maybe I'll end up an applied mathematician working in industry yet, because yeah, I'm definitely coming around. Definitely coming around to it in a way that it wasn't before. Milne's online notes, yeah, that would probably be a good place to look. Oh, yeah, Kedleya. Yeah. That's a good suggestion. I think he's got a couple really nice books. Yeah, I think I've opened that one before, and yeah, I can't speak from experience, but it looks good. Um, Definitely looks like a good read, 100%. What if today I had to start over again with zero knowledge? What books, papers would I read to get back to the same position you are now? Wow, that's an awesome question. Um, Fun fact about statistics I might enjoy: information theory has a cohomology theory. What? Hold on a second. Hold on just a second. I will get back to the really good question, but Juan Pablo uh, thesis cohomology information topology of statistical systems, a cohomological approach. What? This is interesting. Wow. Cohomological approach to information theory. Amazing. Amazing. I mean, it kind of makes sense. It kind of makes sense. Um, uh, like in the set, local to global things. Like I could imagine, yeah, there's something there about like local information versus global information and going back and forth. Axiomatic Q deformation of Shannon's theory. Very interesting. Yeah, I want to read this. I feel like it's just not enough time. I need to work on my paper, damn it. But this seems really cool. I have not really done any work on stochastic differential equations. I started reading a little bit about stochastic calculus stuff over the winter break because I was like, oh, maybe I'll go into finance after. Which also, yeah, mathematical finance. There's actually really cool stuff going on there. There is interesting math there, 100%. 5 years ago, I never would have said that, but now I think that's the case. Yeah, if I had to start today with zero knowledge, what books and papers would I read to get back to the same position? Well, I mean, what do you mean by zero knowledge? Because, I mean, if I couldn't do 2 plus 2 equals 4, that would really, hey, stop. If I couldn't do 2 plus 2 equals 4, I don't even know what I'd start with there. But let's say we're, let's take as a starting point like calculus or something. And yeah, I don't know. Okay, let's even just frame it down to my research. So let's suppose I have some basic um, um, some basic knowledge in like group theory and topology. Let's even suppose I already have some basic I knowledge in like fundamental undergrad courses. Because those, I think you can also, if you wanted the opinion on what to read for that sort of stuff, then you could start you could start anywhere. There's tons of great references, but where would I start for Langland stuff? I would start with the book by, I don't even know how to spell his name. Oh my God, Henniart. Ooh, sorry, much apologies. I can't English. I can math better than English. Bushnell Leniart. They have a book on local Langlands on GL2. I would probably start here and read that cover to cover. I would definitely do that. Maybe simultaneously pairing it with Getz and Hahn. I mean, there'll be things in this book that, like, okay, if I imagine myself at end of undergrad, like, there'd be plenty of words in both of these books that I wouldn't understand, but making both of those, like, a central focus to begin with, and then, like, those are your main texts that you're trying to chew through, and then, of course, you go look up things in other books if you need reference. But I would definitely... these two books would definitely be part of my main explorations. Mind you, actually, I mean, if I was starting again, I would maybe also try and make more of a push towards the, like, categorical local Langlands picture. So... And I don't even know where to start with that. I mean, I would also probably look at Schultz's 2010 paper where he reproves Langlands for GLN with his, like, new technology. And okay, that's definitely not something you're going to understand. You're actually going to be able to understand at, like, the end of your undergrad. But it's like you should have that, I don't know, on your wall or something, or, like, constantly reference that paper and have that as, like, a goal that you're focusing towards and collecting pieces of information. But actually, I mean, I guess let's stick to the parameters of the question, because there's more to get back to my current research than the direction I would maybe pivot slightly more towards. So another thing is Pramod Achar has a book on perverse sheaves. So I would probably pick up that book sooner than later. So this would be these ones would be more for the representation theory side of things, and this would be more for the geometry side of things. I don't know if this necessarily needs to be read cover to cover for my research. Actually, it's probably better to just read it cover to cover and understand these things. So, yeah, probably these books would be the ones to start on now. Trying to think what I kind of want. There's almost another one I want to toss in for like Langlands type stuff. But yeah, maybe it's good to keep the answer small and have this as could I interview someone who went from pure math to math finance / quant research? That's a great question. I should definitely do that. Yeah. Okay, two things I need. Okay, I have a whole to-do list of things I need to do for this channel. I have some abstract nonsense videos I want to make. Should probably reach out to Professor Hampkins again for an interview. I should definitely find someone who went from pure math to math finance. Absolutely. Do I have any intuition for why perverse sheaves show up in the Riemann-Hilbert correspondence and in D modules? Yeah, these books are expensive to actually buy physical copies of. But there's ways to get access to these texts. That's all I'll say about that. Do I have intuition for why? No, I mean, I don't. I mean, the Riemann-Hilbert correspondence sort of is the connection between. The Riemann-Hilbert correspondence really is the. Like, that statement is the connection between perverse sheaves and D modules, and I don't have a deep understanding of its proof. I mean, it seems to me like you take a D module and I mean, one of the functors that we write from the category of D modules, well, we impose that they're regular holomonic to perverse sheaves, is called the solution functor, right? And so it's my vague understanding, and I don't know to what extent this is true, because, again, I need to better understand the proof of the Riemann-Hilbert correspondence, is that, well, like classically, we have some sort of D module, and you can take some sort of, I think like a HOM into your structure sheaf. And, well, I guess maybe you take like a sheafy HOM. And if you look at this, like the things in here, like if your D module is defined by, let's say, M, right? So say you have some, so dx is like your sheaf of differential operators on X, and you have your partial, differential equations, your partial differential equation, like giving you some like ideal. Then you take this quotient, that's your D module M. Then you take some sort of sheafy HOM, and this can roughly be viewed as a space of solutions. I think, actually, speaking of Achar, maybe let me bring up his book. I think there's even a particular example in here. Where are we? Chapter 5 is D modules. D modules in Riemann-Hilbert. Yeah, I think there's an example somewhere here. Or am I thinking of a different book? Yeah, I might be thinking of a different book. I thought there was one that had an example where you actually realize this. Oh, yeah, here's one example. Right. So, so we have, like, yeah, so here's one particular case. Well, okay, so there's some other stuff happening here with, like, analytification, but you look at this HOM, actually, it looks like you don't even need to take sheafy HOM, but it basically, it can be identified with the space of, right, so phi is basically your differential equation, and this shows you that it can be identified with the space of solutions to your differential equation, right? So now I'm not I don't remember exactly why what happens when we go over to the solution functor more generally from D modules, why that ends up extending to a complex. Well, I guess in this case we are trying to take like sheafy HOM, right? And my vague understanding is that somehow the presence. Why do perverse sheaves exist? Well, because we want some nice like Poincare duality theorems or something, and we have things. We have things that want to be local systems. They would be local systems if your space was completely smooth. But then but if your space is singular, then somehow this is like an obstruction to the thing wanting to be a local system, and thus it instead becomes a complex of sheaves. And so my rough, take this with a big dose of salt, understanding is that, we try and form this space of solutions for our D module, and it turns out like it wanted to be a sheaf, but sometimes it just ends up being possibly because of the presence of some sort of singularities or something, it ends up being a complex of sheaves instead. Okay, so this is my rough understanding as someone who needs to better understand all of this stuff. But yeah, a chart is a great place to go look at this overview. Yeah. Actually, this is an exercise I should do. That seems like a very good exercise. Or the other, yeah, this version down here. This is a great exercise. Maybe I'll go and make one of my good friends in the office do that exercise with me. Too much stuff to do during the day. Too much interesting stuff always. Yeah. Anywho, what else is there to say today? Any other questions from chat? The coffee is getting low. I could just end it here and get some actual work done this morning. So maybe that's what I'll do. Thanks for joining me, everyone. Start of a new week. We all got lots of theorems to prove moving ahead from today. So go prove them. Now's the time. And tell me about all of your wonderful proofs that you came up with